This video is a continuation of section 7 of chapter 1 in your textbook. It will cover significant figures and calculations as well as uncertainty in measurements, and it will also cover section 8, which talks about unit conversions. So all measurements have a limited number of significant figures. So these guys show up in scientific measurements, and we report them so that we know that every digit is certain, and then we estimate the very last digit, and we call that the uncertain digit. So when you're in a lab setting and are actually taking the measurements, you want to pay close attention to what instrument you're using. So on different types of equipment, so be it a graduated cylinder or a scale or something different than that, there's going to be different demarcations. So for graduated cylinders, it might be marked every 1 milliliter, or the really small, like the 10 milliliter graduated cylinders, are marked every 1/10 of a milliliter. So the scale here, we've got markings for every gram. And here we've got markings for every 0.1 grams. So it's important that you read what the scale says. In this case, we can see that it's pretty close, a little over 1 gram. If you look carefully, you can see that it's not halfway between the 1 and the 2 gram mark. Switch to an arrow so you could better see it here. So we see that it's just kind of gracing the 1 gram mark, definitely not halfway and not close to 2. So we know that it's 1 gram. So this one is our certain digit. The next digit, so the 10th place, is the one that you estimate. So they estimated here that it's 1.2 grams. So again, we're not sure about that digit. It could be 1.1 grams, it could be 1.3, 1.4, we're not sure. So that's why we call that our uncertain digit. So on this scale, we see that we have markings every 1/10 of a gram here. So each of these little lines is 0.1 grams. So we know that it is at least 1.2. So we have 1.1, 1.2. So it's between 1.2 and 1.3. So again, we estimate it's a little more than halfway. So they estimated here as 1.27. So again, that 7 is our uncertain digit. The other two we know for sure. All right, so based on that information, I want you to look at this graduated cylinder and kind of estimate what the volume of this liquid is. But before you hit pause, I'm going to briefly talk about this word here called meniscus. So you can see that this water kind of has a concave shape here. So this happens because water has a strong attractive force with the glass, so it's trying to cling to the glass as much as it can, so it kind of climbs up a little bit. So to read properly on for water or a different fluid in a graduated cylinder, you want to read to the bottom of the meniscus. All right, so we're going to look to this little concave shape here, and wherever the bottom of that concave shape hits, that's where you're going to read your volume. So hit pause, try to figure it out, and then I'll join back with you. All right, so again, we're going to look at this graduated cylinder. We see that we have markings for 4 and 5 milliliters, and then we've got little markings in between. So this is 4.1, 4.2, 4.3, and so on. So these are marked to the 10th place. So here we count, so we've got 4, so we know our first digit is 4. 1, 2, 3, 4, 5. All right, and we see the bottom of our meniscus is somewhere between 4.5 and 4.6. Okay, so we estimate 1 digit beyond. So based on our answer choices here, we know that it's 4.5. Those are our definite digits, and then we estimate 1 digit beyond. So we have our answer as C, 4.55 milliliters. So it's not A because, you know, this guy isn't marked every 10 milliliters. 4.5 is closer, right? But again, because this is marked every 0.1, we want to estimate to the hundredths place and not just call it to the 10th place. And letter D, that's estimating beyond what we can actually measure. So this would only be correct if we had markings for every hundredths place. So then we'd estimate to the thousandths place. So obviously that'd be really hard to read on a graduated cylinder of this size. So our answer again is C, 4.55. So we're going to be using significant figures in a lot of calculations. So we've got 4 rules here that you need to commit to memory in terms of how to count significant figures. So we'll go through them one by one. So the first one says that all non-zero digits are significant. So essentially, if it's 1 through 9, it's significant always and forever. Don't have to worry about it. So those aren't tricky. What gets tricky is the zeros. So you see there's a lot of, if it's a 0, it may or may not be significant. So we're going to go through those one by one. So the first rule is that interior zeros are significant. So essentially what this means is if you have zeros in a number sandwich, we count them as important or significant. So if you have numbers like 101, the 0 is in between 2 non-zero numbers, so we count him as significant. Again, with 2009, again, these guys are sandwiched in between 2 non-zero numbers, so we count them both as significant. The third rule is that leading zeros are not significant. So say we have a number like 0.000275. So the leading zeros in this case are these 4 zeros that kind of lead the way. All right? So these are not significant because essentially we could wipe them out with scientific notation. All right, so here's that same number in scientific notation. Again, I didn't include the zeros, so they are insignificant in this number. Rule number 4 may be part of the reason that people get frustrated with chemistry. So it's stated that trailing zeros may or may not be significant. So sometimes they are, sometimes they aren't. It just depends on the situation. So trailing zeros after a decimal place are in fact significant. So I have these numbers here. So I've got 1.000. So here these guys are zeros after a decimal point. So these guys are all significant. So this means that I know this number to the thousands place for certain. And then I have 275.300. Again, these guys are behind a decimal place. They're also behind some more numbers. But these guys are both significant as well. So this guy has 1, 2, 3, 4 significant figures, whereas this guy has 1, 2, 3, 4, 5, 6 significant figures in total. The final point of this last rule is that zeros at the end of a number without a written decimal point are ambiguous and should be avoided by using scientific notation. So say I have the number 100. So there's no decimal place in this number. So it's kind of unclear as to whether or not these zeros are significant or not. So a way to fix that is to either put a decimal place behind the 100, or if you do indeed mean for all 3 of those numbers to be significant. The other way is to write it in scientific notation. So you could say 1 times 10 to the 2 if only the 1 is significant, or 1.00 times 10 to the second if all 3 are supposed to be significant. And just a sidebar, in scientific notation, all of the numbers that show up in the coefficient, so that's that number that shows up before the times 10 to the whatever power, are significant. So some numbers are called exact numbers, and they have essentially an unlimited number of significant figures. So these guys are not measurements. You just kind of know that these values are 100% the number that they represent. So if you count and there are 146 people in your classroom, you know that there are exactly 146 students. So that number does not have significant figures assigned to it. Definitions are also said to be exact. So we know that 1 centimeter is 0.01 meters. So again, that's something that we know to be exact. And then integer values as found in equations also fall into this exact number. All right, so counting significant figures, once you get the rules down, isn't so bad. But now we need to take that and apply it to calculations. So there are 2 sets of rules for this. So the first is when you're multiplying or dividing, and the second is when you're adding or subtracting. So we'll start with multiplying or dividing. So when you multiply or divide, the answer should have the same number of significant figures as the measurement with the fewest number of significant figures. All right, so a definition is fun, but it works a lot better if you can see it done out in a problem. So here we've got 1.275 times 3.5. So the first thing you want to do is go through in each number and count how many significant figures you have. So in the first number, you have 1.275, all non-zero numbers, so we've got 4 significant figures in that number. 3.5, we've got 3 and 5, so you've got 2 significant figures there, and I abbreviate SF as significant figures. So you want to go through and just put that number in your calculator, do the multiplication, and write your answer. So we have 4.4625 as our answer. Now we can count here, and we see that this has 5 significant figures. Okay, but our rule says our result, our answer, should have the same number of significant figures as the measurement with the fewest number. So we've got 4 and 2, so that means we want to round this guy to 2 significant figures. You always start from the left, so we're going to count this guy and this guy, so both 4s, as significant. Everything else is uncertain. So then our rounding rules apply, just like they did in elementary school, where if the number next to your last significant figure is 5 or above, you round up. If it's 4 or below, you stay the same. So this number becomes 4.5. You would do the same thing for division. Now for adding and subtracting, we're looking at decimal places. So your answer should have the same number of decimal places as the measurement with the fewest number of decimal places. Alright, so again here we've got 17.572 minus 4.50. So again, go through and count how many number of decimal places. So that's numbers behind the decimal. So here we've got 1, 2, 3 decimal places. Here we've got 2. So our answer in this case should have 2 decimal places, or 2 numbers behind the decimal. So again, you put it in your calculator, don't round yet. So we've got 13.072. And again, we want to round this to 2 decimal places. So we're going to keep the 0 and the 7. The 2 is going to cause that 7 to round down or stay the same. So our answer should be 13.07. When you have multi-step calculations, you want to not round until the very end. You're going to keep track of all your significant figures and then round at the very end. Alright, because this is chemistry and we talked about measurements, every measurement requires a unit. So you can do operations, so add or subtract or divide or whatever, on units just like you can with numbers. So if you're adding or subtracting units, you can only do so with like units. So if you have 2 lengths, they both need to be the same unit before you can add or subtract them. So if you have 2 lengths that are in centimeters, you just add them together to get the total length. If one, say, is in meters, you need to convert the other to meters before you can get your answer. Any unit, however, can be multiplied or divided. So if you have centimeters times centimeters, we get centimeters squared. So this is a unit of area, so length by length. If you have centimeters divided by centimeters, those units cancel out. And you can take grams divided by milliliters to get grams over milliliters, or grams times milliliters to the -1 power. This is one of our units for density. So I talked about conversion factors briefly in the previous video, but calculations involving units may require the use of a conversion factor. And again, these can be measured quantities or they can be exact. So these guys are written first as equalities. That's where you write that, say, 1,000 grams is equal to 1 kilogram. And again, remember there's lots of different ways to express similar expression. So you could write this in scientific notation to say 1 times 10 to the 3rd grams is equal to 1 kilogram. Or you could say that 1 gram is 1 times 10 to the -3 kilograms. Or 1 gram is 0.001 kilograms. So that's just 4 ways to write essentially the same thing. So my advice is to pick one that works for you and stick with it and don't try to go back and forth. That'll only lead to confusion. So we take these equalities and can write them as conversion factors such that our units will cancel to give us the desired unit. So everything that follows here is kind of lumped into the category of dimensional analysis. And we're going to keep doing this throughout the entire semester. So make sure that you get this part down pat. So your goal here is to arrange the conversion factors. So those are the expressions, the equality expressions written as fractions, so that a given unit cancels to give your desired unit. And that's what they ask for in the problem. All right, so you start with your given unit, what they give you in the problem. You write your conversion factor such that your given unit is in the denominator so that it cancels with what's in the numerator. And that leaves your desired unit up at the top, which would be your answer. So again, you might have to do this many times and hop a few times to get to your desired unit, stringing together a bunch of conversion factors, but you can just take them one at a time. So say, for example, what is your height in meters? So I, for example, am 5'5". So I first need to figure out how many inches I am total. So I'll convert 5 feet into inches by using this first conversion factor here. So I put 1 foot on the bottom, 12 inches up top. So I get 60 inches in 5 feet. I add to that the other 5 inches of my height. So I'm a total of 65 inches tall. So now I've got to take that into meters. We can look at the other conversion factors that they give us here. So I have that 1 inch is equal to 2.54 centimeters. And I have that 100 centimeters is a meter. All right, and now I need to get to meters at the very end. So I always like to look at all my conversion factors and kind of see how I can string them together. So I know I have inches here. So I'm going to use this second conversion factor. Again, I put 1 inch on the bottom so that it cancels with the inch on the top. So that means my 2.54 centimeters goes on the top here. So my inches cancel. At this point, you can stop and solve if that makes you more comfortable. I tend to string a bunch of these together before I solve. So again, pick which one works for you and go with it. So my next step is to take centimeters, and I need to get to meters in total. So here I have this very final conversion factor. This is just a metric conversion. So I put my 100 centimeters on the bottom, my 1 meter on the top, such that my centimeters cancel and I'm left with meters at the end. So I am 1.651 meters tall. If we think back to significant figures, we start with the 65 inches that I was given, or that, my height is in inches. That's going to be 2 significant figures. So this rounds to 1.7 meters. I don't seem very tall in meters. Here's another example of this if your height was 5'9". So that's 69 inches. So they go through the same process as I do. Again, given unit, cancel on the denominator there with your new given unit, cancels there, and you're left with meters on top. So that's your goal. You're just working through like a puzzle. You want what's on the top to cancel with what's on the bottom. You want to make sure that you end up with the unit that they ask for in the problem. All right, so one last problem before we end here. So we've got carpet costing $15 per square yard. You've got a room that's 120 feet squared. How much is it going to cost you to carpet your room? So take a time out. Try to work through this one on your own, and then we will solve it together in just a second. All right, so let's go through this together. So again, I always like to kind of differentiate what they give me versus what I need. So here is what I am given. They tell me that carpet is $15 per yard squared. I also have a room that is 120 feet squared. At the end, I need to know how much money it's going to cost. All right, so I've got to assimilate all of this information and get it into just dollars. All right, so if I'm given more than one thing, I always start with the least complicated thing, so the one that's not a fraction if I can. So I'm going to start with my 120 feet squared. All right, so I have feet squared. I look at my conversion factor that they gave me in the problem, and I have yards squared. So I know that's not going to work. So I first have to figure out how many feet are in a yard. This is probably common knowledge, but we know that we have 3 feet in 1 yard. I guess common knowledge if you grew up with the imperial system of measurements. If you're metric, maybe not so much. But there's 3 feet in 1 yard. All right, so I have this information, but I also know that my feet and yards are squared. So if I just tried to write it like this, I can see that my feet aren't going to cancel. So 1 foot will cancel, but I'll still be left with, feet times yard, which is kind of a weird unit. So if I need to change the powers on my units, I can do that. So here I would need to say square my feet to get my feet squared to cancel, but I also have to square the unit. That's very important. And then what you do to the denominator, you also have to do to the numerator. So again, if I have to square the unit, I also have to do it to the number, and if I do it to the bottom, I have to do it to the top. If it helps your thought process, you can also just kind of write it after you do out the math. So instead of writing 3 feet squared and then 1 yard squared, you can just write 1 yard squared and then already having squared the 3, 9 feet squared. Either way is fine. Okay, so now my feet squared will drop out and I have yards squared, and that's what I have in one of the given conversion factors. So I will just do that. Put that on the bottom, yard squared on the bottom to cancel with yard squared on top here. And the $15 goes on the top. So here now I just need to multiply and divide and get my answer. So after putting it in my calculator, I get $200. So 120 divided by 9 times 15. So that's not really a bad price for carpet. Alright guys, so that is the end of this video. So go back through, you can watch these as many times as you need to, go back through and read the chapters. Also go through and work through the problems that are embedded in your chapters. They're great because it gives you the answer, and sometimes it kind of shows you how they worked through the problem. So it's great if you're struggling. Alright, thanks guys.